acid-base chapter out in front of us, taking a look at acids, bases, salts, and that whole process called neutralization. We've received our new note pack, and we've been working on the process of writing down some of our vocabulary words. But we're actually going to begin today talking about the way that we measure concentrations of acids and bases, and specifically the ions that give us acidic solutions are hydrogen ions, and the ions that give us base solution are hydroxides. And I think about when an H and an OH, those acid ions and base ions combining, we begin to see what the process of neutralization is all about. So I have a PowerPoint slide that I've just run off, and I'm going to share with you some of those notes. And the slides that I have and we'll be taking notes together on, you of course are going to be filling in your note pack. So I've got mine open to page 3, where we see the title here, Acids, Bases, Salts, Neutralization. And we're going to just start talking about some things and working some sample problems together. So as the journey begins in acid-base chemistry, we have to realize that acids and bases only exist in solution. They have to be dissolved in water. So the story begins even before we can talk about properties of acids and what makes them a family, or property of bases and what makes them a family. We talk about the whole process of creating a solution. And I know solutions are another name for homogeneous mixtures, and therefore they have what are called solutes and solvents. The solute dissolves into the solvent. Solute is what goes in, and the solvent does the dissolving. So as we think about acids in water, the acid ion is the solute, the water is the solvent. So all of our solutions in this particular chapter will be dissolved in water. So acids and bases exist in aqueous solution. What are the ways that we can measure? And that's where we'll begin with ours, to measure the concentration of our acids and bases. So the term concentrated versus dilute. When we measure concentration, I've been sneaky all year long, and I've been using this capital M called molarity. The concentration of a solution, we'll need to record this in our note pack. I'll read it out loud for us. It says it's a measure of the amount of solute that is dissolved in a given quantity of a solvent. How much solute goes into a certain amount of solvent? You may certainly pause the video if you need longer times to write these definitions and start again when ready. But the term concentration, is it concentrated or dilute? To me, concentrated means we've got a high amount of solute compared to the solvent. A more dilute solution has more water compared to the solute. When we dilute a solution, we pour water on it. Concentrated solutions contain a high amount of solute compared to the solvent, and a more dilute solution contains a low amount of solute compared to the solvent. We need to record these definitions. The term concentration, it's measuring the amount of solute dissolved in a given quantity of solvent. We'll write the term concentrated, one that contains a high amount of solute, versus the word dilute, one that contains a low amount of solute, and we compare those to the amount of solvent. Of course, these are qualitative terms. Qualitative because there are no numbers involved in them. So when I think about a concentrated solution compared to another, it might very well be dilute when compared to yet a third solution. So we need a better way to give the reader more information about the term concentration. And that term is called molarity. Big M is our symbol. It is defined as the number of moles of solute per liter of solution. Big M is defined as the number of moles of solute per liter of solution. Moles per liter, big M. When we see a big M, that term is read as molar. So this term here, 12M, we read that by saying that's a 12 molar solution. Now I know exactly there's 12 moles of solute in every 1 liter of solution. Quantitative measurement uses numbers. Qualitative does not use numbers. The terms concentrated and dilute, we claim those to be qualitative because there's no numeric value assigned to them. Quantitative, the term molarity. And friends, there are other ways that we measure concentrations of solution. It's molarity that's the most commonly used and the one that this course will focus on. So let's begin taking a look at how easy molarity problems are. And perhaps, let me put this slide back up, and I'm going to encourage you to write some what I would call margin notes. Round little buddies might be helpful. If the term molarity is defined as moles per liter, this round little buddy might help us in finding the solution. If we're asked to solve for molarity, that's the one we cover up, moles per liter. If we want to know the number of moles, that's the one we cover up, molarity times liters, or mole over molarity to find a volume. You know, another helpful round little buddy you should record as a margin note. We know that the relationship between grams and molar mass gives us a unit called the moles. And I can clearly see this to be the common link between big M, molarity, and how much we actually weigh out to create a solution. So moles per liter, molarity, grams over molar mass gets us moles. Two familiar formulas. We just wanted to see them in like a visual way for visual learners like me. Now let's take a peek at a sample problem. I'll read it with us. We have a calculator out, we have our notepad, and we'll read problem 1. A saline solution, that's a fancy word for saying salt. A saline solution contains 0.9 grams of sodium chloride. I'm going to record that piece of information. And we're going to place that into 100 milliliters of solution. What's the big M, the molarity of our solution? Well, just from our previous slide, we know big M, molarity, to be moles of solute per liter of solution. We also know that moles can be found by knowing the mass, measured in grams, over the molar mass. Sometimes I say the word formula weight. So this to me looks like a two-step journey. We've got to convert our grams to moles and place moles per liter of solution. So I'll begin by writing 0.9 grams of sodium chloride. We're going to use its molar mass to convert it into a mole. The mass of 1 mole, I'm going to add up an Na and a Cl, and I just know that one by heart. It's 58.5. Hit with me. 0.9, the mass of our NaCl, divided by the formula weight of 58.5, and we get a number of moles, 0.01538. I'll just write all those decimals. Step 1, grams converted to moles. Well, it's a mole map problem. Grams converted to moles. Step 2, now that we have the number of moles, we can use our molarity formula. Big M is the number of moles of solute we just found. And now remember, it must be in a liter. So 100 mils, you divide by that 1,000. Milli means 1,000, and that's 0.1 liter of solution. Moles per liter. So while I still have that on my screen from the previous calculation, I'll divide it by 0.1, and we get a number. That number tells me 0.15, let's round a little bit. Big M, the molarity of our sodium chloride solution. There is exactly 0.154 moles of sodium chloride per liter of solution. The very definition of molarity, moles per liter. We'll read a second problem together. Suppose we have a solution that has a volume of 2 liters and contains 36 grams of glucose. What's the molarity of our solution? What's the molarity? Big M, moles per liter. Moles is grams over formula weight or molar mass. So we see a journey to take. We're looking for the big M, the molar concentration. We know the value of the volume to be 2 liters. We have a little mole map work to do. Step 1, let's convert the grams to moles so we can use it to plug into our molar mass formula. We are given 36 grams of the sugar called glucose. We know to convert that by dividing through by its molar mass. And that was given to us. That was very nice. 180 grams per mole. The number of moles of solute can be found by hitting 36 grams divided by the molar mass of 180, and that value is 0.2. And now that we know the number of moles to be 0.2, we can use our molarity problem. Our formula, big M, the number of moles per liter. Well, we just found 0.2 moles of C6H12O6. And the number of liters given to us in the story problem was 2. 0.2 divided by the 2 liters gives us a 0.1 molar glucose solution. Turning our grams to moles, moles divided by volume measured in a liter finds this concentration unit known as molarity, moles per liter. Let's see what's next. We have a solution who has a volume of 250 milliliters and 0.7 moles of table salt. Well, this story problem's even easier. Given 0.7 moles of table salt, in a liter of solution, notice how I moved the decimal over, we find our big M, our molarity. We'll take the number of moles, 0.7, we'll divide it by the quantity 0.25 liters, and we find that this solution is 2.8 molar units, 2.8 molar sodium chloride. The concentration of our solution. How many moles of solute are present in 1.5 liters of a 0.24 molar sodium sulfate solution? Well, we have a little different target here. We'd like to know the number of moles, but it's the same formula. We know molarity to be moles per liter. They gave us molarity. They gave us liters. We're looking for the number of moles. So let's plug in the numbers that we do know. Concentration was 0.24 molar. How many moles per liter? Think about that round little buddy. We just drew that a moment ago. If we'd like to know moles, that's the one we cover up. Molarity times liter gets us the number of moles. Cross multiply and find X. The math is as simple as taking molar units of 0.24 times the volume of 1.5, and we find 0.36 moles of sodium sulfate. Molarity cross-multiplied by liter. Molarity times liter finds the moles of solute. And our identity there was sodium sulfate. These aren't so bad, are they? Let's read on. How many moles of ammonium nitrate are in 335 milliliters of a 0.425 molar ammonium nitrate solution? Think about what we know. Round little buddies are helpful here. Big M, molarity times liter, can pull out moles. We know that grams over molar mass is our relationship there between these. So I'm seeing a way to ultimately bring it to grams. We need to solve for moles first and then do a mole map problem where we can convert that out to grams. The number of molar units, 0.425, big M. How many moles of solute per liter of solution? Notice I moved my decimal, changing the milli to a liter. 0.355 liters times the molar units, and I'm finding 0.142, I'll carry one more decimal, that's moles of ammonium nitrate. Cross-multiplying molarity times liter finds me moles. Now that becomes what we know down here. How do I turn a mole into a gram unit? Well, we'll use the molar mass. It's just an old mole map problem. So we know the number of moles. I want moles to cancel, so I know it needs to go on the bottom, and I'm going to need a molar mass of our salt called ammonium nitrate. Let me add that up for us. 14 on the nitrogen, but I count 2 of them. There's 4 hydrogen, and 16 times 3 for the 3 oxygens contribution to the weight. Looks like the molar mass is 80. So now I have the number of moles, 0.1424, times that molar mass, and we've converted our grams into moles. 80 times the number of moles of 0.1424 and 11.392 grams of ammonium nitrate, the mass of our solute that's contained in a 0.425 molar solution when we have 0.335 liters of that. Molarity times liter found mole, mole times molar mass found the number of grams. Let's take a quick peek here. How many moles of solute? And that solute is calcium chloride. We know we have a 2 molar calcium chloride solution. How many moles would contained in a 0.25 liter solution? Molarity times liter finds the number of moles. So 2.0, forgot the 0 there, 2 times 0.25 is 0.5 moles of calcium chloride. And an old mole map problem can find the number of grams. 40 on the calcium, 35.5 is a chlorine, but there's 2 of them. So that molar mass is 111. So 0.5 moles times 111, and that comes out to be 55.5 grams of calcium chloride. The mass that we've measured out to make a 2 molar solution of calcium chloride. Mole times, or molarity times liter is moles, and we can see that moles times molar mass pulls out our gram unit, how much we measure out on our scale. Oftentimes, when I buy acids or bases from the chemical supply company, they come to me in a very concentrated bottle. And that makes sense to me because I don't want to pay for water being shipped through the mail. When I buy hydrochloric acid, for instance, I buy it in 18 molar. 18 molar is very concentrated. You take the lid off and you see a little steam come out. But when we generally run labs, we usually run anywhere from a 0.1 molar. I mean, if we need a really concentrated version, I might use a 6 molar, but certainly much more dilute than when I take it out of the stock bottle. Making a dilution is a very practical application When we go to the stock bottle and it's more concentrated than we need for our particular lab, our recipe's calling for more dilute version, the word to dilute just simply means we got to add water. When we add water, we dilute a solution. So when we make dilutions, we're adding water. What that means is we're making a solution less concentrated by diluting it with a solvent. So to dilute means add water, and the solvent for us is always water. So if I think about when I say solvent, note to self, in the lab, if I'm diluting, that means I'm going to pour in water. So the dilution reduces the moles of solute per unit volume. It doesn't change the number of moles of solute in the solution, it simply changes the amount of water that it contains. When we calculate the molarity of a new solution after we've diluted it by adding water, we use a formula. The molarity and volume of the first solution is equal to the molarity and volume of our second after we've added water. We increase the volume by adding water, therefore decreasing the molarity. The concentration unit should go down when we add water to increase the volume. So the dilution formula, MV equal MV, the original molarity and volume, set equal to the new molarity and volume after we've poured water onto the solution. And again, these are very easy. We'll be given 3 of the 4 variables and asked to pull out the missing variable. So suppose we need to create a new solution. We're running an experiment and what we have on stock doesn't match what the recipe calls for. How many milliliters of a stock solution? Stock simply means what do you have on hand? It's in stock. It's on your shelf. It's in the storage room. Prepared already. In stock. What's laying on the shelf? You go to the shelf and this is what you're pulling off. That's called a stock solution. It happens to be 2 molar in strength. But when we run our experiment, we need 100 mils of a 0.4 molar. Let me set up the scenario. This is what we have in stock. This is what we need for the lab, for the running of this experiment. We need 100 milliliters of a 0.4 molar solution. But all we have on hand is a 2 molar. How do we make this solution? Now look at this algebra. As long as the units are the same on both sides of the equal, we're good. We do not have to have liters. If I put a milli in, I get a milli out. Molarity and milliliters work fine for this algebra. So I'm going to hit for the amount of the concentration I need to measure out. So let's hit. I'm going to hit 100, hit the side without the variable. So we have 100 times 0.4 divided by 2. And we get a number. That number gave us 20 milliliters. How many milliliters do I measure out? Well, let me make sense of that. I measure 20 mils of the stock solution. So, like, just imagine I've got a grad cylinder, I pour in the stock solution to the 20 mil mark. We need 100 mils. Remember this? We need 100 mils. Well, so far in this cylinder I have 20 mils. I'm going to add water up until the 100 mil mark. You could say I'm going to add 80 milliliters of water, or practically speaking, as I'm pouring in, I just add water until I see it reach the 100 mil mark. Stirry stir, swirly swirl, and now what do I have? Well, I have 100 mils of a 0.4 molar. That's what I needed for my experiment. When I took my 2 molar bottle off the shelf, I poured out 20 mils. To dilute means to add water. I added water to create that target volume of 100 milliliters. It would be 80 more mils to get up to the 100 mil mark. And I've done a process called a dilution. Let's consider a second example. How many milliliters of a stock solution of 4 molar potassium iodide would you need to prepare 250 mils of a 0.76 molar potassium iodide? So this looks like what I need for the experiment. This is what I have on hand. That's called a stock solution. What's in stock? Well, I know my dilution formula, M1V1 equal M2V2, where M1V1 is what we have on stock. So this is the stock solution. Over on this side, this is what we need for the experiment. So when I go to my stock bottle, which means it's sitting on the shelf in my storage room, it's 4 molar. It's more concentrated than what we need. I need to create a solution that's 0.76 molar units, and I need to run the lab. I need 250 mils of it for the recipe. For whatever reaction I'm conducting, this is what I need. This is what I have on hand. How much do I measure out? So let's hit for V1, starting on the side without the variable. We have 250 times 0.76, divide by, what was that, 4. And we get a number. That number, 47.5 mils. Now what does that mean? It means we're going to measure 47.5 mils of the stock solution. Let me visualize. I have a graduated cylinder or a beaker, whatever is a precise measuring tool. From the stock bottle, I pour in, up to the grad cylinder, I pour in 47.5 milliliters with the utmost accuracy I can muster, 47.5 mils of the stock solution. But to dilute means we add water. So I look at my grad cylinder and I find the 250 mil mark. Remember, that's our target volume. I literally add water up to the 250 mil mark, stir it up. Let me catch that sentence up. I measured out 47.5 mils of the stock solution, and now I'm going to add water to the 250 mil mark. And it's just always good advice, stir. Stir it up to create a uniform solution, and we've created our target molarity. Let's try one more. Suppose you need 250 mils of a 0.2 molar solution. The only supply of sodium chloride you have is a 1 molar solution. How do we create our solution? Describe the process. Now I just plugged this in. I have molarity and volume of a first scenario. This is what I need for my lab. And this is what I have on hand. That's called our stock solution. Let's hit 250 times 0.2, divide by 1, and we get a number. That number is 50 mils. What does that mean? Make sense of that number. Here's my grad cylinder. Very carefully, I measure out. I'm going to measure out 50 milliliters of my stock solution. So far, I'll just put a period there. I've got 50 milliliters of the stock solution, which is the 1 molar of sodium chloride, sitting in here. Don't forget the word dilute. We need to dilute it means we got to add water. So first of all, I poured my stock bottle solution in, but I'm not done. We need a target volume of 250 mils. So now I'm going to add water to create a total volume of 250 milliliters and stir. The resulting solution will be 250 mils of a 0.2 molar, and that's exactly what we need. By adding water, we've diluted a 1 molar all the way to a 0.2 molar. It's much less concentrated, and that's the same as saying more dilute. At this point, we have finished. Just put our notepad up. We have finished here talking about our concentration unit and the great foundation of the molarity, of how we go about measuring strengths of acids and bases. We needed this lesson before we could even begin talking about acids and bases. At this point, you are to stop your Moodle lesson for the notepad and begin working on your homework, the practice sheet on molarity problems that will be due and corrected tomorrow.